probably more useful or more relevant, which we'll see here in a little second. Because we have those two pieces and we form that cyclic intermediate, or that cyclic acetal. The one on the right is a cyclic acetal, but it's an internal cyclic acetal as opposed to an external one, if we will. Okay, kind of makes sense? So what do you guys think? You can identify acetals pretty well? Okay. Should have, but I forgot to provide the carbohydrates so you could see a carbohydrate acetal. I'll try and remember to do that for the next lecture, which probably means I won't do it, but I will try to remember. So as we talked about in here, our reaction favors the product with that first one because our electrophile is very electrophilic. Okay. Electrophilic, so we have an electronic effect because the hydrogens can't stabilize that positive carbon. We also have a steric effect. The hydrogens don't block the nucleophile from attacking. Okay. When we move to the next one, that reaction heavily favors the reactants because those carbons can share electrons inwards. So we have an electronic effect that stabilizes that carbon, makes it less electrophilic. We also have the steric effect. Those carbons are larger, blocking that position. Okay? And that next one, we also have the added benefit of entropy favoring the reactants. Okay? So all of those things stacked make that next reaction not valid. The last one favors pretty universally the final product of the acetal. Okay? We have no entropic effects here, and once we form the hemiacetal, which is relatively easy to form, equilibrium-wise, we have our nucleophile now insanely close to the electrophilic site that it can lock in. Okay? What we have here is what's known as kind of a chelation effect, which if you've used EDTA in any of your labs in the past, and like 152, which probably everybody used or did in EDTA lab, it wraps around metal ions and it bonds to the metal ion in 6 different locations. So it bonds really tightly because any one of those is easy to break. But as soon as you have 2 or 3 or 4, it's now really hard because any one breaks but the other 3 are still there. The odds that all break at the same time, very unlikely. Same thing can happen with our acetal. Because those structures are now connected, if one breaks off, well, it's still close enough that it could come back. If we look at the acetals in the top 2 cases, if one breaks off, it can float away entirely from it, and we don't see it anymore. So it can't make that connection back as easily. So the cyclic acetals tend to have a lot of things going for them, and that tends to be where we encounter the acetals most frequently, is in the cyclic structures, much less so in non-cyclic ones. Right. So product favored, reaction favored, 5 and 6 membered rings, generally product favored. Yeah, we can always encounter exceptions, but for the most part, that works. Right? So all that should have been reviewed. We're all good with that? Okay. So acetals, as I mentioned already, do show up in biochemistry. From an organic perspective, we can also use them as what is known as protecting groups. They're equilibrium reactions, so they go forward and backwards. Okay, so we can change the properties of our structure really quickly to do some chemistry, right? Which is something you've already used in first semester OChem. We took advantage of acid-base chemistry to change the solubility of a compound to make it change phases that we can then isolate and change it right back. So if we have that reversible chemistry, we got something that we can use in the lab to purify or prevent that chemistry from happening. That's the primary goal of acetals. Okay. Synthetically, we don't use them. They aren't that big of a deal. As protecting groups, they're pretty phenomenal. So if I take a look at the structure shown, I can go through and make the acetal with decent yields by making the cyclic acetal, so I have to use a diol. That gives me a 5-membered ring for my acetal. That's relatively stable, relatively likely to form. If I want to ensure that most of it goes to the acetal, what do they also do? They remove water from the product side, so that shifts the equilibrium. They also added an acid, because the acid facilitates or lowers the activation barrier for that first attack, okay, facilitating the acetal formation. If I don't want the acetal, or I want my carbonyl back, then all I have to do is add water. It'll now very quickly and easily reverse back to the carbonyl on its own. The carbonyl is more stable, if you will, than the acetal form. Okay? So it's a neat little reaction that we can swap back and forth. And I don't think I came up with an example one for it, so let's draw one. Why would we care about this? Okay, well, let's say our structure had a double bond on it. And I want to run the reaction where I now make this structure. Yeah, we're going to go ahead and work with this, even though it's a bit big. What type of reaction happened there?
Addition.
Cool, addition. I had not thought of that answer, but that is valid. It is an addition reaction. What did you add? We added 2 hydrogens, or hydrogen gas. Okay. How do we add hydrogen?
Simple reduction.
Okay. This is now referencing the type of reaction that I was aiming for here. This would be a reduction reaction. It is technically an addition. So we can do it via a reduction. Okay. To do that, I would need my source of hydrogen. That's my H2. H2 is too small a molecule to react on its own, so what do we need? H2 and a catalyst. Okay. Typically something like platinum, palladium, or nickel. Those are all ores. And so what's happening is we're taking the pi bond and reacting it with hydrogen gas. Okay. Which pi bond do we want to react? The alkene. Okay. Is the catalyst selectively looking for alkenes? No, it's selectively looking for pi bonds. Why is that an issue if we try to throw H2 and platinum and palladium at this? I've got 2 pi bonds. I'm not going to end with the carbonyl. I'm going to end with the alcohol. Okay? So if I used those reagents, where I would end up with, and this is officially now chapter 19? Right? 17, 18, 19, right? That we're looking at? Yeah. That reaction or reagent is officially chapter 19 with carbonyls. We haven't seen that yet. Okay, so we will see that in a little bit. So how can I get that black result? How can I reduce just the alkene? Okay. I will do it in steps. So I will first go through, make the acetal. Now that I'm in the acetal, I only have 1 pi bond. Now what can I do? Well, now I can add my H2 and platinum, or palladium. The result will be the reduction of the alkene, and it won't touch the carbonyl because there isn't a carbonyl to reduce. Okay? To get to my final product, what do I now have to do? Add my water, my acid catalyst, and I would now have my product. So I can use the acetal to protect the carbonyl functional group to do some other chemistry. Okay? If we think back to all the reactions we've done so far, when we've done our reactions, even our synthesis, they may have been multiple steps, but there was really only 1 functional group present that would react. So when we did our multiple steps, we didn't have to worry about these other things. If you move further through synthesis, you'll have larger and larger structures that have multiple functional groups. If those functional groups react with whatever reagent you're adding, well, they're going to react, and you're going to end up getting a mixture of products. So what we can do is one of 2 things. The first is set up protecting groups. The use of protecting groups prevents chemistry from happening at that site or with that reagent. And as long as we can easily reverse it, which is by definition a protecting group, we're good to run. Okay? The issue with that is that I really only wanted to do 1 step. I wanted to do, let's call it our purple step. That one step. To do that one reaction on the left, this was my target. To get that one reaction to occur, I had to do 3. Okay. So that's like saying for me to take one step forward, I also have to take 3 steps around. That gets a bit redundant and repetitive very, very quickly. Okay? It also reduces efficiency. It's now taking twice or 3 times as long to initiate that one reaction. So a reduction in efficiency, more time, all of those things are bad things. Okay? One, it's causing, you're now paying someone who's got an advanced degree in chemistry to do a bunch of reactions that they shouldn't have to be doing. That's a waste of money. It's now a waste in chemicals. Well, what happens with all those chemicals when you're done with them? They're waste. So not only are you paying someone to do a bunch of chemistry that they then follow up and just undo, but you're now also paying to take all the stuff that they used and throw all of it away. That's insanely wasteful. And so for a synthetic process or a synthetic mind of view, that is a horrible concept, and it's taken on a new acronym. Okay? Lydia and Alexis will know that new acronym. Or that new name. What is the name for chemistry that protecting groups are not? Because your chemistry instructor at the other campus is famous for this chemistry. Everything she does focuses on it. All the waste is bad because we have to dispose of it. Where are we disposing of it? We send it to the company. Okay, so what does the company then do with it? They put it in the ground. They put it in the environment. Protecting group chemistry is bad for the environment. It is not green chemistry. Green chemistry takes the process of protecting groups and says that is an awful concept. I'm going to redesign my experiment or my setup such that I do not end up at this point where I'm trying to do a reduction and I have 2 options. I change the entire paradigm shift on how I do that. Okay? And instead of having a carbonyl and an alkene at any one instant, I will make sure that the carbonyl appears after I've gotten rid of the alkene. Okay? So that both those functional groups are never in the same place at the same time, which means I don't need a protecting group. That usually requires a lot more thought, which is also why you get a lot of resistance to green chemistry techniques, because it requires that synthetic chemists have to think significantly harder about how to avoid issues like this. Okay? So as far as green chem goes, this is a horrible synthesis. Okay? As far as old school chemistry goes, it's great, it's common, everybody uses it. Okay? So I just want you to be aware of that when thinking about our protecting groups. Which then takes us into an entirely different topic. Lovely segue, Mike. Our hydrolysis of nitriles, not entirely different. Okay? We are still using oxygen as a nucleophile. But what is the polar pi bond I'm now attacking? Is it a carbonyl? No. What am I attacking now? I'm having that oxygen attack the carbon of the nitrile, pushing the electrons outwards. The end result, or an intermediate result, is our amide functional group. Okay? Is the nitrile still a polar pi bond? Is nitrogen more electronegative than carbon? Yes. So it's polar. Is there a pi bond in a triple bond? Yes. Is there a polar pi bond? Yes. All of the chemistry still follows the same rules that we've already done. Oxygen can still attack. We can follow this under acidic or basic conditions. Both work, And we can end in air quotes with the imide. Okay? Why the air quotes? Notice that there's parentheses. What are those parentheses saying? We don't end at the imide. Okay? That chemistry will continue forwards. Why is the textbook showing the parentheses now and not saying we continue forward?
We can stop.
We can stop. Okay, why can we stop?
Concentration.
What is different about our polar pi bond to begin with versus the imide functional group?
There's no pi bond.
There's no pi bond in the imide? Okay, so this is our polar pi bond. So that fits. I have a polar pi bond in the imide too, right? Why am I not looking at the next step for this? What's the difference between the polar pi bond as my reactant and the polar pi bond as my product?
There's resonance.
King of subtlety.
What pi bond is it with nitrogen?
What is that nitrogen? What could that potentially do? It could be a leaving group. So far what we've talked about is polar pi bonds with no leaving groups. Okay? The imide has a potential for a leaving group. Okay? Because we haven't talked about the mechanism for what that leaving group can do, they're stopping it here. That's why they're putting the parentheses up, saying that it does not stop at the imide. That is an intermediate structure that will continue all the way down to the carboxylic acid, but to do that involves a mechanism we've not talked about. Is it a mechanism that you could probably come up with? Well, I think that's a good question. Let's do it. So we know where we're ending. Where do we start? So we're at step 2 now. What's the most reactive thing present? No. What's the most reactive thing present? Nope. H plus, the charged thing, is the most reactive thing. H plus. Okay. Now that I have an H plus, now I have to evaluate what's the most reactive thing. Right. After that, what's the most active negative? So we have the concept of potentially the pi bond. Okay. If it is the pi bond, what we're really saying is the lone pair electrons on the oxygen are ultimately the ones sharing electrons out. So we're saying oxygen is more willing to share its electrons than the nitrogen. Why are you vigorously shaking your head, Wyatt? Oxygen is more electronegative than nitrogen. So given the choice between the nitrogen and the oxygen for sharing electrons, the nitrogen is probably the best bet. We could go through and draw out resonance to see that there's just as likely to be a pi bond between the carbon and the nitrogen as between the carbon and the oxygen. Okay? So there really isn't a difference in pi bond characteristics either way. We're really just comparing nitrogen versus oxygen. Nitrogen is more willing to share its electrons. I'm just going to draw this as a pH with what I promised was a Cl there. Now what? So there's a suggestion that the bond breaks. Amine, while neutral, not the greatest leaving group. Okay, and it would leave a positive carbon behind. Okay, kind of a terminal one. Believe it or not, it's not the most horrible one you could have drawn, but it's not particularly stable. I got a nucleophile. Have water attack. What bond's going to break? Carbon nitrogen. Why are you saying the carbon nitrogen?
Because nitrogen's positive.
Nitrogen's a leaving group, right? What bond is connected to the nitrogen? What bond between the nitrogen and the carbon? What bond do we have? A sigma bond versus a pi bond. Which is weaker? Pi bond. We would expect to break the pi bond, and what we end up drawing is this is an intermediate, and yeah, you may freak out at this, that's okay. Don't panic too much. This structure is known as the tetrahedral intermediate. In this mechanism, we need to always show the tetrahedral intermediate. Now what happens?
Lone pair from oxygen comes back.
All right, the lone pair from oxygen could come back.
And then nitrogen.
Now we could eject the nitrogen. We're going to run into an argument here of that potentially not being right in a second. Everybody see that? So we've reformed the pi bond. Anybody have an issue with the structure as drawn?
Positive.
We have the positive oxygen. What can happen? Really, we should be having the lone pair on the nitrogen come up and take the electrons to take us up to that. Notice they showed it as NH3. Why? Because nitrogen is such a prickly atom, and we aren't very consistent when we draw out mechanisms on deciding what charge state we want to show for our nitrogens. Okay? Be it protonated or deprotonated. It depends on what we're trying to show, unfortunately. First step of that reaction was an acid-base step, so that's pretty boring. Second step was
SN2?
it's not an SN2 because what happened to the pi bond? I broke the pi bond, so it can't be an SN2. I lost a pi bond, so it's not SN2. It's an addition, a nucleophilic addition. Oh, like the one we've already discussed. Yes, exactly. It is a nucleophilic addition. What's the next step?
Elimination.
It's an elimination. What kind of elimination? What did we eliminate from the structure? A nucleophile. We've done a nucleophilic elimination. Have we seen that before? No. We've only seen electrophilic eliminations. That's the new mechanistic step that we haven't talked about yet. That's the next unit. Okay? I just want to address it so that you know what's going on with it. You're not fully responsible for it yet, but we will see it. There's all sorts of rules that go along with the nucleophilic elimination. All put together, it's a nucleophilic addition elimination. That's the name of that full mechanism. Okay? So, with that, nitriles do function like polar pi bonds. Okay? We can do a nucleophilic addition to them. Okay? Where you're expected to stop is just the nucleophilic addition. I don't expect you to go through and continue all the way out to the nucleophilic elimination part of it yet. Okay? Which makes it a difficult question to ask exam questions on, which is why we're just going to move on. There's our mechanism. If we wanted to go through and look at the mechanism, we could also do it under base hydrolysis as well. Okay? The addition of HCN, cyanohydrins, end up being a useful molecule here. I can put the C triple bond N on a structure. I can start with my carbonyl and add HCN. HCN is what kind of a species? It's an acid. Okay? So it's a neat species because it self-catalyzes. We have an acidic hydrogen. So what can happen? I can protonate my carbonyl. Once it is protonated, what have I done? Not quite. What did I make? Explain.
We'll have a negative carbon.
Okay, you're right. We made a nucleophile in our nitrile. I had my focus somewhere else. What else did we do?
Activated.
We activated our electrophilic carbon. So we did two things at the same time, made a nucleophile and activated our electrophile all at the same instant. What can happen? Our nucleophilic addition, and we would end up with our cyanohydrin. Cyano because we have that CN structure, and the hydrin because we still have the OH. Okay? We've kind of added water to this. Okay? The cyanohydrin is useful because we can end up getting two reactive carbons right next to each other, which is pretty cool. Okay? It's usually rare to get two active carbons with slightly different chemistry at both those positions. Okay? So that's a neat little reaction to run. The other reason why this is typically shown has to do with that Lewis structure. You almost always see it written out as CN. What is that CN actually? That is actually a polar pi bond. That's your triple bond. Do not forget those extra pi bonds. Those polar pi bonds have chemistry associated with them. We can do the addition reaction that we just talked about to get it down to the carboxylic acid. Again, parentheses on that reaction because that requires the nucleophilic elimination mechanistic step, which we haven't learned yet. Okay? So it's neat because we have two active sites now within our structure as opposed to the one, and I added an extra carbon. Okay? So it is useful chemistry in that respect. Questions? Okay. Oxygen versus nitrogen. So now what we're going to switch to is our nitrogen nucleophiles. What is the difference between oxygen and nitrogen? Oxygen is more what?
Electronegative.
Oxygen is more electronegative, which means it wants negative charge more, yeah. What does that mean as far as the nucleophilic character? Which is the stronger nucleophile? Nitrogen is a stronger nucleophile than the oxygen. And that's the biggest driving force is our difference between our oxygen and our nitrogen nucleophiles. And that's what's going to dictate a lot of the chemistry that we look at when we're looking at our nitrogen nucleophiles. Okay? Size and electronegativity are the two big things that we'd be looking at. Size, they're almost identical, so we don't worry about it. Electronegativity is the big deal. Okay? So when we look at their effective reactivity with carbonyls, nitrogen is the stronger nucleophile. I would expect nitrogen to chase oxygen out of a structure. Okay? With one sort of exception. If we go back and look at our nitrile, the end result of this chemistry was what? What happened? What got chased out of the structure? Nitrogen. Why was nitrogen chased out? Didn't we just say nitrogen's the stronger nucleophile? We started this whole chapter off with that word association game. What was that word I was starting with? Equilibrium. Yes, nitrogen will chase oxygen out in an equilibrium system. In this reaction, what have we done to mess with that equilibrium? We add tons of water to this. That excess in water helps force the reaction in the other direction. Okay? And yeah, you may sigh at me, that's fine. Okay? Yes, that's not pleasant, but that's what's happening. Okay? If I want to force the other direction, I need a ton of the nitrogen source. Okay? There's other things that dictate that this reaction goes this direction. And again, we'll talk about that when we get to that nucleophilic addition or an elimination system. So nitrogen is really just an overactive oxygen. So work out a mechanism to explain this result. Okay. I do say to write it on the whiteboard. How game are you guys to get up and move around? Okay, so I won't make you write it up on the board. Negative and the positive. Most people I talked with seem to want to get rid of that negative first and then do the positive. Why? Well, if it's more electronegative, shouldn't it hold the negative charge? What conditions are we under? Acidic or basic? How do we know it's basic? NH3 is primarily a base. We haven't specified beyond that whether we're strongly acidic or strongly basic. So we should be floating in roughly basic conditions, which would suggest which of those charges should I nullify first? I should nullify the positive charge first. Now what should I do? Fix the negative charge, right? Yes. The second part. Have those electrons pick up a hydrogen. And we'd end up with our alcohol. What picked up the hydrogen in... I should have called these A and B, sorry. And what I'm calling is step 2. What picked up the hydrogen? What took the hydrogen away from that nitrogen? Notice all I've shown in that space there is the electrons going to the nitrogen. What reacted with that hydrogen? Another molecule. What is the property of that other molecule? It's basic because it's sharing its electrons with a hydrogen. Nucleophilic would be something other than hydrogen. We're by definition sharing it with a hydrogen. So we know we have lone pair electrons. What atom is most likely to share those lone pair electrons? Probably the nitrogen from ammonia. Okay. Which means we have a small concentration of ammonium now floating in solution, which is where that hydrogen could come from. It is an insanely small concentration because it's whatever was produced in this first step. Okay? So that is not going to be an easy acid-base step, but eventually it happens. Okay? So also, we're in equilibrium all the way through these, right? We would then get to our intermediate, which is not our final product. Okay? And now we have kind of the issue behind this on how do we move forward from here. Right? Well, what do we know has to happen? Okay. The oxygen needs to leave. Okay. Is that a good leaving group? No. If it's a bad leaving group, it must be forced off. Is there anything that could be used to force it off? Another what?
Another hydrogen?
Another
Hydrogen?
hydrogen.
H3.
We don't have any negative hydrogen, so that's not going to work. What are you now suggesting? Another nitrogen, like we do with the acetals, right? This is effectively a hemiacetal. It's sitting right in the middle of what looks to be a hemiacetal, except it's a nitrogen instead of an oxygen. Okay, and what happened? Well, in the hemiacetal formation, we then did either another acid-base step to make a good leaving group, or we had a second molecule come in to do a backside attack. Okay? We required the second molecule because oxygen wasn't good enough to share electrons as it was already attached to make a double bond. But nitrogen is less electronegative, meaning it is more willing to share electrons, and what can happen? It can initiate and force the hydroxide out. Do we have problems with that? We would have hydroxide, which is a bad leaving group, okay? And we'd have a positive nitrogen, which isn't particularly stable, okay? So those aren't particularly good things. So that step is not particularly favorable. But if it happens, we can then follow it with the hydroxide taking the electrons. We would end up with our double bonded nitrogen and H2O left over. This is all relying on a lot of things happening that are not particularly happy to be happening. To force it to happen, we'll try and remove water and add a ton of the ammonia to help push this along. What else could we do to help force the reaction to happen?
Or base.
A stronger what?
Base.
We could change the conditions under which we went. We could try and go under basic conditions. What's the problem if I go through and make this now basic with, say, sodium hydroxide? Hydroxide's a strong nucleophile. It will compete with the nitrogen. I like where you're going, but it went down a bad path.
Can we make it bulky?
We could try and make a bulkier base to try and facilitate that. Or put it under acidic conditions. What's the problem with putting it under acidic conditions? It'll weaken our nucleophile. Okay? So what do? We make sure that whatever we run, either acidic or basic, we run it under small concentrations, so it's catalytic. It is typically run under acidic conditions, okay, as catalytic. Okay? So some of the nitrogen is weakened, but not all of it. Okay? But by having acidic conditions, what can we do to help out with that second to last step? We could protonate the oxygen to make a better leaving group to make that step easier. Okay. All the way through this, we're going to be like, but if I add acid, it cancels this. Yes. If I add base, it cancels this. Yeah. Okay. Why do we know that this happens? We went into the lab, tested it, and it worked. Why do we know that adding acid works? We went into the lab and tested it, and it worked faster. Okay? So this is why I think this section is frustrating, is everything is dictated based off of equilibrium. You just have to do it. Okay? This is why we started the whole chapter off with equilibrium, and I don't care what's wrong or whether you think it should happen. It does. Do it. Which, yes, is frustrating and different than any other section that we've looked at. But everything that we're looking at within this is an equilibrium. Each of those equilibrium steps is what's controlling how the reaction works. And it's now a question of what is more stable, what is in larger or smaller concentrations. And it is all those very subtle things that allow for the reaction to continue forwards. So different from our other cases, we just do it. Okay? Nike. Charge ahead. Just be done. Okay? In the other cases, you were forced to think about why and how it works. Now you just have to do it. Okay? So, acidic or basic. With your nitrogen, you're going to have issues. Okay? When we drew out our mechanisms, you were trying to decide which conditions you were under, and you had to try and make sure that you minimized the formation of other charges. We said it was basic, and yet in our very first step, we showed a positive charge. Shouldn't have been there, because we're under basic conditions. We will have conflicting results. Okay? There isn't anything we can do about that, as depressing as that may sound. Okay? We could go through and do it under acidic conditions, and that tends to be the easiest, okay? But that's just what we have to work with, okay? Acidic seems to be the best. Basic doesn't work so well. So here are some examples We've got a general mechanism on how to go through and predict these. So do it. See what you come up with. Okay? Run it out. If you got to do the mechanism, do the full mechanism, but see what you come up with. Go ahead and bring it back to the front. So in that first one, should be following the pattern from the previous one, and if you drew out your mechanism, one of the things that you should start to notice is that you will lose those two hydrogens. Right? Those two hydrogens get removed, and that's why we have the double bond. So when we move to the next one, you could remove those two hydrogens. Ooh, this one gets a bit tricky because third one's tricky because there's only one hydrogen. Last one, we're actually told to think backwards. Well, I have the NH2, so that's this piece. I know I have a single bond. There's my other nitrogen. What did I lose? Two hydrogens. So there's my reagent that would do that step. Kind of makes sense? For the second one, okay, because it looked like everybody got the first one, why is this not what you guys were drawing? To get that, what did I do? I had the oxygen attack like that. Why did you not do that? Oxygen has more electrons than nitrogen. It has to do with the strength of the nucleophile, not the number of electrons. Right? So the product that you end up getting there, following the same pattern that we've seen with the others, you'd have your double bond to your nitrogen, so you've lost those two hydrogens, and there's your OH. Right? The next one, right? We're forming the double bond to the nitrogen, that's there, and we lose the two hydrogens, but where's the problem? There's only one hydrogen to lose, which means if I form that double bond, what else needs to happen? I have a positive charge on that nitrogen. Does nitrogen want to be positive? No. So it's saying, hell no, this isn't happening, it's taking electrons. What's the problem with that?
Carbocation.
Would then have a carbocation, and carbocations aren't particularly stable. Okay. When I have a carbocation, what reactions should possibly start triggering in your head? Substitution. Well, the nitrogen's there to substitute, share electrons immediately in. So substitution doesn't work.
Elimination.
Elimination. Well, the nitrogen formed a double bond, but I didn't eliminate anything then, right? What am I eliminating to make the double bond?
Another hydrogen.
Sorry, a little squished, but it's there. Okay. The double bond ends up appearing in another location. We still have to lose water. We're losing an oxygen from one structure and a hydrogen from the other, or two hydrogens from the other structure. That was our general pattern. Okay. When we move to that third example, we are still losing two hydrogens and still losing an oxygen. But the two hydrogens are coming from a different location. One comes from the original nitrogen, another one comes from the alpha carbon to that imine structure. The result is that we get a double bond next to an amine. A double bond is known as what? Double bond is known as what? Between two carbons? An alkene. A nitrogen is known as an amine, and I end up with an enamine. Yep, that is a name. Okay, that is also a name of the reagent that you guys are using in lab today. You're going through enamine chemistry. Okay. The very last one, we have the reagent. Right? What would we expect to happen once we've got that structure? What are we then adding to it? We're adding sodium hydroxide in the presence of water. So what can possibly happen? I got a strong base. What can that strong base do? act as,
Nucleophile.
so it could do a nucleophile, and it could come in and do an attack like that, and we end up going right back where we came from. But we don't. We do something else. So it could act as a nucleophile, or it could act as a base. Where is there something partially acidic? What hydrogens? Yes. We have a negative carbon. What? Why would I ever want a negative carbon? That sounds awful. Right? But what could that negative carbon then do? React with water in solution to put a hydrogen on it. You'd be like, okay, well then I have a final product, right? What is still floating around? OH, what is still floating around? Another hydrogen, what can happen? It can attack again. Those electrons shuttle around. These electrons shuttle to our carbon. And I know you're like, oh my God, what's going on? He's out of space, he can't draw anymore. I'm going to draw backwards. What's your product look like? I end up with a cycloalkane. What kind of reaction did I do beginning to end? Yes? Keep going. Yes, it is an addition. It's a reduction. We've done reductions of carbonyls before and we ended at alcohols. Why is this one different? We did reductions before and ended at alcohols. Why is this one different?
There's no alcohol.
There's no alcohol. There's no functional group anymore. I've reduced the carbonyl entirely off the face of the structure. Right? Maybe I needed that carbonyl so that I had alpha chemistry accessible to do some chemistry out there. But then I want to get rid of the carbonyl. What could I do? I could use that sequence of reagents to completely remove that functional group in entirety from the structure. Okay? So synthetically it could be useful. I could want to do that. Okay? Why would that reaction go through all of that? I mean, that's a lot of stuff. Okay? To go all the way down to nothing. Why would it do all of those extra steps? Remember, nitrogen is not particularly acidic. Why is the base removing that hydrogen? What is driving this reaction to make that product?
Thermodynamics is different.
The alkane is a little bit more stable than the carbonyl. Fair enough. I will give you that. Okay, because we've lost the pi bond. Not enough to drive that reaction. Do you want a hint? That's not the only product. What's the other product? We end up forming nitrogen gas, N2. That's what drives this reaction. Nitrogen gas bubbles out of the solution. We don't have a reversibility anymore. All of those steps that I showed, those removing hydrogens, yeah, those are horrible equilibrium steps. Very unlikely to happen. But if for some slight chance it happens, and then it happens a little bit more and a little bit more, then snap, boom, nitrogen gas comes out, what happens? Equilibrium is now non-reversible. I will slowly start to build all the way across until I've converted all of it across to the alkane. Okay? That's our equilibrium issue that we have to worry about. Okay? Make sense? That chemistry, we would expect no way in hell that's possibly going to happen, right? But it did. And somebody found it. And chemistry that no way in hell should possibly happen, but somebody discovered did happen, get someone's name. It's known as the Wolff-Kishner Reduction. Okay. You take NH or hydrazine, NH2 or N2H4, react that with your carbonyl under basic conditions in the presence of water, you end up kicking out nitrogen gas. Okay? A reaction near and dear to my heart because it was the first reaction I did as a graduate student and it failed miserably. I blame the patent. Every time I keep reading the patent being like, that step makes no sense. That is a completely nonsensical thing to do. That explains why all of my reactions went south. Because some jackhole wrote the patent in a way that prevents people from following it. Okay, so that is the Wolff-Kishner reduction. It is officially a Chapter 19 reagent following Chapter 18 chemistry. Okay? Remember I said we were going to come back to this? We got this big, lovely beast of a thing going on here. Okay? We look in the upper right-hand corner. Okay? We had our substitution chemistry for our carbonyls. That was our Chapter 10 stuff. Okay? That would be left-hand corner, for those of you counting. Right-hand corner, strong base. Again, more substitution chemistry. Okay? If we drop now down into the left, in fact, pretty much the entire bottom quadrant. That's half, by the way, not a quadrant. What's happening? Okay, so let's take a look at our aldol. Moving to the left here. It says under basic conditions. So if I'm under basic conditions, what happens? Well, I have an enolate. What is the chemistry of the enolate? It was a nucleophile. The electrons come back down. We have a nucleophilic carbon. We just looked at nitrogen acting as a nucleophile, attacking what? What did the nitrogen attack? Carbon of? Carbonyl. And we previously looked at oxygen as a nucleophile attacking carbonyl. And before that, we even looked at carbons and hydrogens attacking carbonyls. As long as they were nucleophiles. What is an enolate? A nucleophile. What can that nucleophile do? It can attack a carbonyl. Sorry, Lisa. I don't mean to be laughing at you. But the oh my gosh was kind of nice. It is effectively the carbonyl reacting with itself a second equivalent. Okay. Once we have a nucleophilic carbon, that nucleophilic carbon can do all sorts of damage. Okay. That's where we encounter our aldol chemistry, and then it gets 50 other names depending on who discovered it, okay, or who's addressing it. It is still the enolate chemistry. It is the enolate attacking a carbonyl. If that carbonyl is an aldehyde, we have an aldol. If it's a cyclic reaction, it becomes an intramolecular aldol. If it's attacking an ester, then it's a claisen. If it's a cyclic ester, then it's a Diekmann condensation. Okay? But it's all the same chemistry. You're now looking at the carbon nucleophile of a carbonyl attacking now a carbonyl. Okay? So if we went through and looked at that, this is just kind of the setup behind it. I am done, so we'll have to stop there. We'll pick up with our aldols on Monday. Our breakdown of the name, because we've been looking at weird ones. We looked at an enamine, which was an alkene and an alcohol. We had the enol, which was an alkene and an alcohol. We now have an aldol. Ald because We will have an aldehyde, all because we will end with an alcohol. If we push that all the way through to reveal our final answer, almost our final answer, what do we have? We have an aldehyde connected to an alcohol. That's why it's called the aldol. You'll notice there's a couple extra boxes. Those couple extra boxes is because we very rarely ever stop at the aldol.